Hello Gators, this is 5.6, determining concavity of functions over their domains. 5.7, using the second derivative test to determine extrema. A graph with this shape is called concave up. I want you to notice that the tangent lines are below the graph. They go from left to right. It's negative, 0, and then positive, which means the slopes of the tangent lines are increasing. Increasing means that its derivative, the derivative of the first derivative, must be a positive value because the second derivative describes the rate of change of the first derivative. Also, a graph with this shape, concave downward, going from left to right, the slopes are positive, 0, and negative. The tangent lines are above the graph. The slopes are decreasing, which means the second derivative is less than 0 because the second derivative describes the rate of change of the first derivative. One more time. If f is concave up, then we say f prime is increasing. Increasing means that the second derivative, which describes the first derivative, is greater than 0. So the second derivative being greater than 0 is telling you something about the function f, that it is concave up. If f is concave down, f prime is decreasing. Decreasing means that what's describing the decreasing, which is the second derivative, is less than 0. The fact that the second derivative less than 0 describes the function f as concave down. Let's take a look at an example where we find the intervals of concavity. I took the first derivative, I took the second derivative, set it equal to 0 to find the places where the second derivative is equal to 0. And then I would like to find the values at these intervals. So I'd like to find the value at this interval, which is negative. I'll just choose a number, -3. I'm going to put it in the second derivative. I'm going to put it everywhere where there's an x. And when I put -3 in here, I'm going to find that the second derivative is greater than 0. I'm going to choose a number in this interval, which is 0. I'm going to put 0 right into here, and I'm going to find that the second derivative is negative. I'm going to choose a number in this interval, which I will choose 3. I'm going to put 3 in here, and I'm going to find that it's a positive value. We don't have to actually find the value, just whether it's positive or negative. Okay, so now we knew this was positive, and negative. Now we can declare that it's concave up at those intervals because the second derivative is greater than 0, and we can declare when it's concave down because the second derivative is less than 0. The graph of the sine has lots of concavity. You can see it's concave up in this interval, concave down, concave up, concave down. These blue dots have a name. Those blue dots where there is a change in concavity are called points of inflection. A point of inflection has to be a defined y value, and the second derivative changes at that point. In other words, a point of inflection is where the graph changes concavity. Here are two common mistakes that students make. Assuming that the second derivative equal to 0 means you have a point of inflection. Let's take a look at this graph. F of x equals x to the 4th looks like this. If I take the first derivative, it looks like this. If I take the second derivative, we have 12x squared. If I put 0 into the second derivative, I get 0. But the fact that the second derivative is 0 doesn't guarantee I have a point of inflection. The other mistake is assuming that when the second derivative does not exist, that you have no point of inflection, and that's not true. Let's take a look at this function, x to the 1/3 power. Here's my first derivative, here's my second derivative. The second derivative does not exist at 0, and yet it clearly shows that at x equal to 0, we have a change in concavity from concave up to concave down. Let's take a look at typical things that the AP gives, which are graphs. So here's the graph of f prime. So I'm going to take a look at the slopes of the tangent lines along here, and I'm going to put it in a little chart for myself. So all these derivatives here are negative. So this is going to be a negative in this interval. All these derivatives are going to be positive, so it's positive in this interval. All these are going to be negative, and all these are going to be positive. Notice how I said that this second derivative does not exist because that's a corner. This second derivative does not exist because it's a corner. This derivative did exist. It is equal to 0. Over here, notice that I don't have a first derivative graph. I have a second derivative graph. So now I'm not really looking at slopes of tangent lines, but just the sign, the SIGN, whether it's positive or negative. So over here, I know that the second derivative is 0. Over here and over here, all these are places where the second derivative is equal to 0. It sits above the x-axis, so this is going to be positive. This is going to be negative, all this little wiggle here, and this is above the x-axis, which is positive, and then negative. So I've determined whether it's positive or negative. Now I can go ahead and talk about whether it's concave up or down. Concave down when in the intervals where it's negative, and concave up when it's positive. Same over here. There's one more thing I do need to talk about, and that's points of inflection. And the points of inflection are these places where the sign changed, and over here where the sign changed. Let's now determine whether the line to this graph is above or below the graph, and why. Okay, so I'm going to take the first derivative, which is going to require that I use the product rule, and now I'm going to take the derivative of the first derivative. The derivative of this will be negative e to the opposite of x minus, and then I want you to notice that this thing right here is exactly the function again. So I'm just going to put a minus in front here, and I'm just going to copy the derivative inside. E to the opposite of x minus x e to the opposite of x. So this part in red, I'm just recopying my derivative. And after I do that, I can substitute the number 1 in for everywhere there's an x. And then I find that when I simplify, my value is negative. So the tangent at x equal to 1 lies above the graph because at x equal to 1, the graph is concave down. Let's take a look at identifying the extrema in this graph right here. So at this point right here, I know something about the first derivative. The first derivative right here is equal to 0. And I also know something about the second derivative. The second derivative, notice it's concave down, so that's less than 0. And this is a relative max. On this relative min, again, the first derivative is equal to 0. And the second derivative, because at that point it's concave up, that will be greater than 0. And this is a relative min. So when these things happen, then we can decide whether it's a relative max or a relative min. So the second derivative test says this: if the first derivative is equal to 0 and the second derivative is greater than 0, then it's a relative min. If the second derivative is less than 0, that means it's concave down, then it must be a relative max. So let's use the second derivative test to find the relative extrema for this function. So I took the first derivative, and these are all my critical points. So the second step is to take the second derivative, which is going to be 12x squared minus 4. And then what I want to do is I want to evaluate the second derivative of each one of these. So if I put 0 in here, I'm going to get less than 0. If I put a 1 in here, I'm going to put a 1 in here, and that's going to be greater than 0. And if I put in a negative 1, I'm going to have greater than 0. So these tell me, along with the fact that I have a tangent line that's equal to 0, and now I've determined whether that tangent line is sitting above a hill or below a valley. So now I can go ahead and actually say that I have a relative max at x equal to 0 because the first derivative is equal to 0, the second derivative is less than 0. And then we can say the same thing about our relative min at x equal to 1 and x equal to negative 1. All right, I'd like you to stop the screencast and see if you can do this problem. And here's the answer. I took the first derivative, and found my critical points, took my second derivative, evaluated my critical points, and noticed whether it was greater or less than 0, which made it, then I was able to determine whether it was a relative max or a relative min. If there is only one critical point, then the critical point is an extremum, a max or a min. Then it is also an absolute extremum. So let's take a look at this problem. I'm taking the first derivative, which requires the product rule, and then I want to find the critical point, so I set that equal to 0, and I find one critical point. Now I have to take the second derivative, which means I'm going to take the derivative of this portion right here. I'm taking the derivative of this part right here, which is going to be this. And then I am going to take the 1/4 in front and then take the derivative of this inside, which is the product rule. Okay, once I do that, I'm going to have this, and then I can substitute my -4 in there. And when I substitute my -4 in there, I find that inside the parentheses is positive, outside the parentheses is negative, which is less than 0. So this is a point that's sitting on concave up, and so that point is going to be an absolute minimum because the curve is going up at that point. The second derivative test for relative extrema. Let's be careful. This test does not require a second derivative number line. It does not find points of inflection. It is used to find relative extrema. So use f prime to find the critical points. Plug those critical points into the second derivative to analyze concavity and determine whether you have a relative max or min. The second derivative test does not work if the second derivative is equal to 0. So you go ahead and use the first derivative test if that happens. This is the end of the screencast.